really struck by the beauty of the statements and also sometimes how horrible the actual arguments are. But one instance where this is well understood and totally, we have a really natural correspondence is the so-called geometric Satake equivalence, which I'll explain towards the end. And at the very end, I'll give an application, which is in some sense just to justify my own existence. I just basically want to explain something that I find nice, and I feel that there's some obligation to state something that you've done at the end, which I will do. So I just want to remind you what Fourier series are. So if we take a 2-pi periodic function on the reals, then we can write it. It has a Fourier series. Something like A0 plus the sum Bn sine nx. And so, of course, this is not quite equality. And what we're doing is we're decomposing our general periodic function here. So you could think about this as, for example, the noise of a violin into fundamental frequencies. So these sine waves and cosine waves are roughly what a tuning fork produces. So if I give a public lecture on these things, I explain that you could probably make a device, I have no idea if anybody's tried to do this, where you have a whole lot of tuning forks lined up of different sizes, and if you bang them all at once, it sounds like a violin. Seems unlikely that you can actually do this, but this is in some sense what Fourier series tells us that we can do. And somehow this is useful throughout science. So Fourier was originally interested in the fact that, for example, he starts off his book by commenting on the fact that if you dig down a few feet into the earth, then the temperature fluctuates rather a lot with the days, whereas if you go down not very far, then suddenly this fluctuation totally disappears and you can only tell the seasons, for example. And he's interested in how heat dissipates in materials. And in order to solve the heat equation, he comes up with Fourier series. And I just want to discuss 3 examples of this. So the first one is, this is an analogy that I learned from Jim Arthur. So I'm not sure if you know this story, but Fraunhofer took the light from the sun and shone it through a prism. And what he noticed is that the light, so normally we expect to get a rainbow from natural light. We expect all the spectra to be there. But what he noticed was that there are these black missing lines. And what he suspected is that these were the absorption spectra of elements in the sun. And this was then confirmed by others about 30 or 40 years later. So that's the example of Fraunhofer lines. Another example is I went to this talk of Noel Cressy from Wollongong about a few months ago, and he's one of the world experts in how to work out the CO2 distribution around the world so that you can get a very good map of CO2 in the atmosphere. And they rely on a few testing stations, but mainly on a NASA satellite that orbits the Earth. And what it does is it just looks down at the surface of the Earth and does a spectral analysis on the light coming from the surface of the Earth. And remarkably, by that spectral analysis, you can tell differences of a few parts per million of CO2, which I found totally remarkable. And a third example is, so this is the analogy that I learned from Jim Arthur, which is that when Fraunhofer shone the sun's light through a prism, he could tell something about the sun that's very non-obvious via other means. And so we can see the kind of Langlands correspondence as shining the light of number theory through a prism, and we see things that are not obvious otherwise. So the classical example of this is the Riemann zeta function. So there's Riemann's explicit formula, which expresses the prime counting function, i.e. how many primes are less than a given magnitude, in terms of the zeros of the zeta function. And so you can really think about the zeros of the zeta function as being the kind of Fourier transform of the prime numbers. So this is the zeta function. So what has this got to do with representation theory? So a 2 pi periodic function, we can see we have the exponential map. And so any 2 pi periodic function will descend to a function on the circle, and any function on the circle will pull back to a 2 pi periodic function. So a 2 pi periodic function is the same thing as a function on the circle. So complex numbers of norm 1. And when we phrase it in this way, it's very nice because these kind of cos nx and sine nx just become the functions z goes to z to the n. Okay, so the real and imaginary components of these complex functions now give us our fundamental frequencies. And we have this fundamental decomposition, which is essentially the Fourier transform, which is the statement that the L2 functions on S1 can be written as a completed direct sum in the sense of Hilbert spaces of CZM. Oops. Anyway. Okay, so I remember when I first saw this statement as a third year student, I just thought it was wrong. It's really two different, very different things being the same. And we can ask, why are these functions so important? So why are the kind of fundamental frequencies present in the Fourier transform? Why is it so good to express a function as as a linear combination of sines and coses? Why not some other choice of functions? So somehow what this is saying is that in this Hilbert space decomposition, these are somehow special. And why are they special? So one answer would be to say that the sine and cosine functions are solutions for the simple harmonic oscillator. But a more fundamental explanation, I think, is to use representation theory. So when we do this, we notice that S1 is a group under multiplication. So given two complex numbers, we can multiply them. Given two complex numbers of norm 1, we can multiply them. And that these functions occurring on the right here are actually homomorphisms. So they're group homomorphisms, which is just expressing the silly fact in this case that z times z prime to the m is z to the m times z prime to the m. So, and in fact, over here we have all continuous homomorphisms of S1 into C star. So in fact, all continuous homomorphisms are of this form. So I'm a representation theorist, and in representation theory, we study representations, which are basically group homomorphisms from a general group G into GLNC are what we call representations. So what's going on here is we can say why these fundamental frequencies, why are they so important? They're so important because they are the irreducible representations of S1, of the circle group. And a kind of slogan, which is useful, is that irreducible representations so just in other parts of mathematics, there's building blocks for all representations, which are the irreducible representations, those that do not omit any invariant subspace here. And these are the irreducible representations are kind of the fundamental frequencies of the situation. And this is basically why we care about irreducible representations so much. So if you're given, for example, in computer science, the space of states would be something like all 0-1 combinations in memory, and where we have some function on this space of states, and then we have, for example, the fast Fourier transform or something, which is linked to the irreducible representations of something like z mod 2z to the million or something. Okay. Please interrupt me if there's any questions. I'm not particularly concerned about getting to the end of this talk. So just another example of a very important feature here is that because S1 is abelian, all the irreducible representations that occur up here are one-dimensional. But as soon as we go to a non-abelian group, there will be interesting higher dimensional representations. And just to illustrate this, I want to discuss briefly spherical harmonics. So here we have the special orthogonal group, which is the group of Euclidean transformations of 3 space, so rigid Euclidean, it's essentially rotations of 3 space through any axis. So this is the special orthogonal group SO3, and this acts on S2. So those vectors in R3 of norm 1, and here you see a very poor attempt to draw a sphere with an iPad. And so what this philosophy of of representation theory and harmonic analysis tells us is that we should decompose this function space of L2 functions on the sphere according to SO3. So you can think about this space as all the measurements we can do on the sphere, and we would like to decompose this into the smallest possible SO3 invariant measurements that we can do. And here's some pictures. So what happens here is you get different packets of irreducible. So this would be the constant functions. And this, I'm not sure if this will show up, but here are the packets, the irreducible representations. So this would be the packet of functions of degree 1. This would be the packet of functions of degree 2, etc. And if you are, it's a nice little thought experiment. So this is an attempt that Wikipedia has made to depict what these functions are. And it's a very nice little thought experiment to work out what on earth is going on in these pictures. But so we know from many different fields of mathematics that somehow spherical harmonics are the analog of Fourier series on the sphere. So this yields the kind of and these are also extremely useful in many different areas of science, the spherical harmonics. So now comes a scary slide, which is, I just want to explain in very broad terms what the Langlands correspondence is. And I'll first be extremely sketchy, and then I'll be very sketchy. Okay? And that's all I can offer you, I'm sorry. But I will try to explain with some precision the absolute simplest example of the Langlands correspondence. So I won't be totally sketchy the entire time. So the Langlands correspondence is an attempt to link two different worlds, namely the world of arithmetic and the world of analysis, or particularly complex analysis. So the first kind of incarnation of this that we see is things like the prime number theorem and the zeta function. So here are some questions that we ask in arithmetic. So how are primes distributed, for example, in the integers or in rings of integers or in function fields? These are all extremely classical and very, very interesting questions. So existence of primes in arithmetic progressions, etc. And these questions are addressed by following Riemann's extraordinary paper by passing to the world of complex analysis. So the first case of this is the zeta function. And then when we want to look at primes in arithmetic progressions, we look at Dirichlet L functions. When we want to consider, for example, primes in number fields, then we look at Dedekind zeta functions. And then Artin comes along and explains to us that Dedekind zeta functions have a beautiful product expansion. And the pieces are called Artin L functions, etc. Other questions, for example, how many extensions does Q have? It's an extremely basic question that I think we're still miles away from understanding in Galois theory. And Diophantine geometry, which is an enormous subject, but very, very classical problems are still extremely interesting. So imagine that I take a polynomial in a few variables, f, and I ask, how does the number of solutions of this polynomial, so I take a polynomial with integral coefficients, and I let the prime vary, and I ask how many solutions does it have at mod p as p varies, and this is conjecturally linked and sometimes known to be linked to questions over this side. And somehow the Langlands correspondence is a web of conjectures to connect these two sides, which passes through representation theory. So on both sides of this, the questions kind of break up into pieces, and those pieces are matched on both sides via representation theory. So in order to explain this very simple instance of the Langlands correspondence, I need to explain in rough terms what a reductive group is, and in rough terms what the Langlands dual group is, which I'll do now. So if we have a compact Lie group, there's a canonical process known as complexification, which gives us something called a complex reductive group. And we can go back the other way by taking a maximal compact subgroup. So just as some examples of this. So if we take the circle group, this is the maximal compact inside C star. If we take something like, let's say SU2, so this is Hermitian transformations of C2 of determinant 1, and this corresponds to SL2C. This is the maximal compact inside SL2C. And something like, for example, the unitary group, UN, so this is Hermitian unitary transformations. Hermitian transformations. This is the maximal compact inside GLNC. Okay. And there's a canonical way of going from here to here called complexification. And
why is your U in Hermitian transformations? Surely it's unitary transformations.
Sorry, unitary transformations, yeah. So basically, the result of doing this to a compact Lie group gives you all complex reductive groups. So there's various ways of saying what a complex reductive group is, but in this talk, I just want to think of it as the kind of companion over C. So this is an algebraic group over C. Which is associated to a compact Lie group. So I'll mostly use the terminology of compact Lie groups because I feel that this is more broadly known. But why do we care about reductive groups? So complex reductive groups are more flexible. So the reason is that they're defined over the integers. So it's very non-trivial, but they're defined over the integers. And so we can talk about things like GLNZ and GLNFP. So there's these beautiful universal objects corresponding to any compact Lie group that are defined over the integers by some polynomial equations. So for example, SLNZ is just the set of n by n matrices whose determinant is 1, which is a polynomial with integral coefficients. And so we can talk about a whole raft of groups starting from one reductive group. But as I said, I'll mostly phrase things on the side of compact Lie groups. So I'm headed to define the Langlands dual group, but first I need to recall in rough terms that reductive groups are classified by root data. So how do we kind of go about understanding a compact Lie group? We choose a maximal torus. So this is isomorphic to S1 to the n inside it. And then we have associated to this these two fundamental lattices. So this already showed up when we were discussing the Fourier transform. This is exactly what was occurring on the right-hand side of our Fourier transform, namely the homomorphisms from S1 to S1. So we have these two lattices, and these are dual lattices. Okay, so they're both non-canonically isomorphic to z to the m, or z to the m once we choose such a nice identification. But this identification needs this identification. But if we don't make any identifications, these are canonically dual lattices, which is extremely beautiful basic fact. And then I don't want to go into it too much, but we look at how this torus acts on the Lie algebra of our Lie group, and this gives us the notion of root and co-root. And then the basic theorem is that this data of these two dual lattices plus the roots and the co-roots, this gives us something that's called root data. So this gives us the root datum of our and this determines This determines K up to isomorphism. So just a silly example, if we take, I mean, the first example would just be to take K to be S1. And so then we'd have no roots or co-roots, and we'd just get the integers as our lattice. Here I've taken G or K to be SO3. In that case, a maximal torus is all rotations through a fixed axis. And this is S1. And then if we work out the roots and co-roots, so in this case, the roots would just be plus or minus 1 inside Z. So this, in this case, this chi would be isomorphic to Z. And here's another example where I've taken K to be the compact symplectic group. And in that case, T is a, sorry, SP4. And in that case, T is a two-dimensional torus consisting of diagonal matrices of symplectic diagonal matrices. And we get this nice configuration of roots. So now we come to this kind of mysterious definition, which is the definition of the Langlands dual group, which is, so compact Lie groups and complex reductive groups. So these two things are same isomorphism classes. And then there's a theorem of Chevalley that says that these things are classified by root data. And now the basic observation is that root data have a symmetry. Whoops, there's a typo there. Okay, so I have a lattice and it's dual lattice, and I have roots sitting inside the lattice and co-roots sitting inside the dual lattice, and I can just swap these two things. And so this induces some interesting operation on complex reductive groups. So let's see a few examples. So if we just take S1 or the C star, these are Langlands self-dual. And more generally, the unitary group or GLNC are Langlands self-dual. For a non-self-dual example, SU2 and SO3 are exchanged under Langlands duality, and SP2N and SO2N plus 1 are exchanged, and up to some very minor issues with the center, the exceptional groups are fixed. So in particular, E8 is fixed. Now, the first kind of remark about this, so this notion of the Langlands dual group is absolutely fundamental to the entire Langlands program, but it's not a very, it's not very convincing at this stage, I don't think. All we do is we notice that there's some weird symmetry in our classification, and then we appeal to, so for example, if you'd never met SO2N plus 1 and someone handed you SP2N, what you would do is you would classify its root data, and then you would swap them, and then you would say, Chevalley tells me that there's some group out there that has this root data, but I have no idea what it is. So there's no construction of the Langlands dual group in this language starting from the group itself. So it's rather unnatural. It's just an appeal to it's a rather unnatural definition. It's just an appeal to a existence result. And the other kind of remarkable thing that I understand absolutely zero about is that this has also appeared independently in physics. So I'll just write electromagnetic duality. so that I can sound really fancy. But I understand absolutely nothing about this. But it is interesting that this operation on groups did appear in theoretical physics, independently of knowing anything about the Langlands correspondence. So it seems to be a fundamental operation, and in a few slides' time, I want to explain a natural way of passing from G to G dual. You might not believe me that it's very natural. It's rather complicated, but it turns out to be extremely useful. And I think that we're only beginning to see its power. So here's my caricature. So I said I'd give you a very, very rough outline of what the Langlands correspondence is, and now a very rough outline. So here's the very rough outline. So this is basically, it's saying that arithmetic stuff associated to G, so mapping into G, should be, and this is all arithmetic stuff. So if you want to just think that this is maps from an absolute Galois group into G, that would be a great thing to start with. So this should be in some kind of correspondence, maybe one-to-one, maybe many-to-one, maybe many-to-many, to irreducible representations of the dual group. So we're looking at maps. So the kind of a key feature here is that kind of maps in, maps out. So we learn in linear algebra that maps into a vector space are the same thing as maps out of the dual vector space. And so, this is some kind of very souped up version of this. So I just want to, in order to position this a little bit, so if we look at the, just to give you some idea of how crazy this is for, so C star slash S1 and the trivial representation. To C star, this corresponds to over here to the zeta function, so Riemann zeta function, and kind of GL2 or U2 is basically the story of kind of elliptic curves, modularity, Fermat's last theorem. So this is two-dimensional Galois representations. Correspond over this side to, so I'm not really explaining to you why you should think about a modular form as some kind of shadow of a representation, but believe me that it is. And I just want to emphasize that this is the kind of arithmetic side. And here there's kind of, very informally, there's not much space. Okay. So in the example of something like GL2, you're trying to fit an incredibly complicated group inside something like GL2 or C star. So you have very little space, and somehow the difficulty is around the fact that you have very little space. This is the kind of analytic side. And there's kind of, over this side, there's too much space. So generally things will be infinite dimensional, and the difficulties are because things are enormous. And the other aspect of this is that this is a duality, and so neither side is particularly easy, or neither side is easy at all. But the great advantage is that you have just two different ways of looking at a problem, and so things that are very difficult on one side generally approachable on the other, etc. Okay. So I'm not sure if it's just a very useful caricature for me to have in mind, this caricature. So I just want to explain why the highest weight theory of compact Lie groups can be seen in this framework. So this is a review of the representation theory of a compact Lie group. So before I explained how to associate root data to a compact Lie group, so we make this fixed choice of a maximal torus, and then we choose a system of positive roots, which gives us a notion of dominant weights. And then the highest weight theory tells us that the irreducible representations are indexed by dominant weights. So here's a picture for SP4. We have this cone of dominant weights, and each one of these lattice points gives us an irreducible representation of SP4. So in the case of S1, this just says that irreducible representations are the same thing as Hom from S1 to S1, which we've seen. So this was the kind of Fourier transform. And for SO3, it tells us, in this case, we have the maximal torus is the same. So Hom from S1 is still Z. And then we have the dominant weights would be those weights that are bigger than or equal to 0. And so the 0, 1, 2, 3 are indexing our spherical harmonics. So this is what our caricature says should be the case. And it's really remarkable how often this works in really complicated examples, but it also works in a very simple example. So this is saying, so we're told that the kind of Galois group of C is C star or S1. Okay. And once you believe this, which of course you would fail anyone in a basic Galois theory course if they wrote this, but once you believe this, then we see that homomorphisms from S1 into K star, into K check, are the same thing as homomorphisms into S. So any homomorphism can be put inside a maximal torus modulo conjugacy, so modulo how many ways I can put it inside the maximal torus. And now this is exactly the same thing as our set of dominant weights, which classifies irreducible representations. Okay. And so you can see the classification via highest weight as being an instance of the Langlands correspondence. So I just want to make one observation about this setting here, which is that here, this is kind of typical of what happens, is that we just kind of worked out both sides. We said that this is equal to something, this is equal to something, and these things happen to agree. And this is typical in this field, that we somehow, for example, we want to show that two sets agree, and then we inject them into some enormous set and then argue like hell that they hit the same elements, for example. And so again, we have this issue where there's no real canonical passage from one side to the other. So now there's this remarkable thing called the geomeric Satake equivalence, which makes a canonical passage. And how is this done? So remember that we started off, this was our kind of Galois side of the Langlands correspondence. So this is homomorphisms into our group G. And we said that this is, so this is, yes, so this is just all homomorphisms from S1 into K. But now what happens is we would like to kind of do, so this is just a set, a rather boring set. And what the kind of brilliant idea is to slightly expand this set and look at, so all homomorphisms from S1 into K, we can instead look at all base loops from S1 into K. This is a very natural expansion of the notion of a homomorphism. And inside that, for technical reasons, we consider the polynomial loops. So these are essentially loops with whose Fourier coefficient, there's only finitely many Fourier coefficients. Just as a kind of, we can classify a polynomial function on S1 as being a function that only has finitely many Fourier coefficients, finitely many non-zero Fourier coefficients. And in the same way, we do that here. And the theorem is that, so this space was identified with all irreducible representations of our dual group. But now we've expanded this, so this is actually, this is homotopic. So this is some reasonable approximation of this space. And basically some category of sheaves on this space of polynomial loops recovers the dual group in this way. So I'll try to be a little bit more precise just in, so more precisely, what we actually do is this space of polynomial loops acquires an algebraic model, and this is called the Affine Grassmannian. So this is a kind of, an analogy to this is the fact that if we take SO3 mod its maximal torus, this is S2. Okay, so S2 is a homogeneous space for SO3, and the fixed and the stabilizer of a point is all rotations through that axis. So this is just a manifold, which can be thought of as analogous to this side, but then we realize that it has another incarnation as SL2 mod the upper triangular matrices, which is P1 of C. Okay. So this infinite dimensional manifold, in this case, acquires the structure of an infinite dimensional algebraic variety. And on this infinite dimensional algebraic variety, we can look at a certain category of so-called perverse sheaves, and this category realizes representations of the dual group. And this sounds very kind of high tech, and I guess it is, but it's the only way that we have of canonically going from a group to the dual group. And the dream is to use algebraic geometry and topology kind of on the left-hand side to study so I guess a basic philosophy is that we should be able to understand absolutely everything about the category of representations of some reductive group over here. And if we can't do that, then there's something wrong. And this philosophy is, I guess, motivated by some
So
work of
why is it canonical? How do you pass? I mean, you've said there's an equivalence, but what is? How does the dual group act? What are the representations?
So if I start with,
How do you pass from a perverse sheaf to a representation? Or vice
so if I take, so basically the basic theorem is that hypercohomology is a tensor functor. Okay, so given a perverse sheaf here, I can take its hypercohomology and I get a vector space. And I get a so the first thing is that this is a tensor category, which is symmetric tensor category, which is totally non-obvious. And then the second statement is that hypercohomology is a tensor functor to vector spaces. And so now I can apply Tanakian formalism and say, okay, this category is equivalent to representations of some group. And then we work like hell to show that this group is the dual group.
I see. Okay, thank you.
Yeah, so I mean, it's complicated, but it's really the only thing that we have. And we have this basic philosophy that everything that we should be able to do over here, we can do over here. But this basic philosophy has taken a long time to realize. So there's this work of Bezrukavnikov that builds an enormous amount of structure in the so-called local geometric Langlands correspondence on top of this equivalence. And then there's recent work of Laforgue, or Vincent Laforgue, that uses this equivalence as the starting point for remarkable work, which gives us a canonical Langlands correspondence for function fields for a general, so a canonical one direction of the Langlands correspondence for function fields. So this work of Vincent Laforgue is totally revolutionary and earning the Breakthrough Prize, for example, I think last year or the year before. Yeah, I think last year. Okay, so now I come to the bit where I justify my own existence very briefly. So I want to say that my interest is so basically we understand this category reasonably well when we're looking at, so for example, when this is the world of a compact Lie group. And my interest is when the characteristic of K is positive. So we're looking at the modular representations of this algebraic group. And we've been in the embarrassing situation for about 30 years where the fundamental theorems on this side we could not prove on this side. The basic structural theorems that get the theory going on this side had no proof on the other side. So this dream, I mean, we want to understand difficult things here via algebraic geometry and topology, but if we can't even do the basics, then we can't even get started. And so there's this meta theorem, which is basically by taking some kind of fixed points under a mu p on this space of base loops, this explains an enormous amount of the representation theory of a reductive group in characteristic P. So so this is one thing that we've never been able to understand on the geometric side. There's also this very long story with Lustig's conjecture. So there's a conjecture that points to this Affine Grassmannian playing a big role. And all the proofs that we have don't involve geometric Satake, which is very strange. And so now we have a proof that does. We get characters of kind of a lot of homological information about this category on the right-hand side by the relatively innocent operation of passing to mu p fixed points on this side. And yeah, maybe I'll just take 2 more minutes. I'm sorry. I mean, I guess you can just leave Zoom if I'm annoying you too much. The basic idea is this very powerful tool called Smith theory. So there's this principle of equivariant localization, which relates stuff on X to stuff on the fixed points. And this is very classical for an S1 action on a compact manifold. But if you have a Z mod PZ action, a kind of discrete circle, then maybe I'll leave it as an exercise to verify that the order characteristic satisfies this relation. And using these ideas, we can get, we can attack a lot of the representation theory of G over here. Okay, so thank you very much.
Cool. Okay, so yeah, thank you very much. So I guess we can clap, do silent clapping. But are there any questions for Geordie?
Why isn't it possible to go the other way around? You said the dream is kind of to use geometry and to understand geometry to get some theorems shown in representation theory, but why don't we go the other way around and try to use representation theory to prove something in geometry which is unknown or hard to prove?
It's a good question. I guess one reason is that we didn't care about, for example, we can do some calculation in representation theory and it can tell us some interesting fact about the singularities of some variety that we've never encountered before. And so the fact that we've been studying the representation theory of a group for a long time and we would like to understand it is one answer. The other answer is that our experience in geometric representation theory is that somehow once you have a bridge, things are easier on the geometric side. And so this is our kind of expectation, which in this particular case was not fulfilled for quite some time.
So, you mentioned Smith theory. So what group and what space?
Yes, so maybe I'll reshare my screen.
Why do fixed points of it? Yeah, okay. So if you could elaborate a little, I'd be very interested.
So, so there's this very simple observation, which is on this base loop space, you have an S1 action, which is kind of by loop rotation.
Yes.
And so in this isomorphism with GT mod, this is just induced by T goes to ZT. It's a very basic action here. And the fixed points of this are the homomorphisms. So, and somehow the fixed point space is kind of boring. So we would think about this as the homomorphisms as being the kind of the Langlands parameters. And so when we just take fixed points, we're just kind of restricting to something like a set. I mean, when we take fixed points in this particular case, what we get is a disjoint union of finite flag varieties, which are not so interesting. So the key one of the key observations is that if you take fixed points under the roots of unity, the pth roots of unity inside S1, you get a very interesting, you get finitely many components.
Mm-hmm.
And they look like, so one example of things in the fixed point locus are those that factor over S1 times mu p. And then there's another set of, there's a whole lot of other components that look like affine flag varieties. And what our kind of main theorem says is that restricting to these fixed points in an appropriate, so restricting to these fixed points loses absolutely no homological information. which is, it seems to me, totally remarkable. So it tells us that the representation theory of this group is just controlled by these fixed points. And so we can deduce a number of theorems immediately from this fact.
Yeah, I'm just surprised that it has anything to do with the finite field situation.
So here I mean the group scheme over FP. So you know, I can also equally write FP bar.
Oh.
But this also tells me a lot about simple representations of G of FP, for example. G check of FP.
Thank you.
Thank you.
I have a
Are there
question.
any other questions?
Yeah, I have one. What if you look at the mu p squared fixed points? Can you say something about that?
I can't see who's speaking, but
It's Jim.
Jim, hi.
Hi.
Yeah, so it's a fantastic question. Yeah, so basically, I don't know. It definitely doesn't work as well. There is some things lost when we do this, but it seems that, yeah. So maybe I just say, great question. We're thinking about it, and it's unclear.
Okay, great, thanks.
Yeah. I guess thank you very much, Geordie, for giving our first colloquium. And yeah, hopefully we'll get the chance to see you again in person sometime in the not too distant future.
Let's hope, yeah.